Hydrostatics, example 4, a drinking straw in which your respiratory system is a pump. So here's some water to drink, and this will be a straw. And suppose we make a closed seal around that straw with our mouth, and this piston will then represent our respiratory system that can expand to decrease the pressure inside this straw, as we see in the next diagram. So the gas that was trapped inside the straw, I'm now showing as a different color since its pressure is now lower than the outside atmospheric pressure of 1 atmosphere. And once we've done that, then the outside air pushing down on the surface of the water with that pressure of 1 atmosphere, it means the water is going to be pushing up on its neighboring water here with that pressure of 1 atmosphere. And this little column of water here rising up this straw, well, that's going to be pushed down by the gas that's still trapped inside the straw. The pressure here is lower than outside, but it's still pushing down on the water in the straw. So the water will feel a net force due to pressure upwards due to the difference between the outside and inside air pressures, and will rise up the straw to a certain height until the weight of the water in the straw is equal to the pressure difference times the cross-sectional area of this straw. So in this picture, we've already drawn the water up 1 full meter. So that'd be a meter-long straw right there. That won't be easy to do. And we've added gravitational potential energy to this water by raising it up higher. So we must have done work on the system. Our respiratory system must have done work to add that gravitational potential energy. So let's look at the work done by your respiratory system. This space here represents the space inside the straw and inside your mouth and inside your lungs as one sort of closed cavity here. And the piston is sort of your chest and your chest muscles that expand when you breathe in. And as your chest expands, your chest pushes outward on the surrounding air that's always around your body. So the net force on this piston, on your chest, will be the sum of 3 forces. One, the force from the outside air pressing inward on your chest. We'll call that force 1 because of the 1 atmosphere of pressure outside. There's the force pushing outward on your lungs from the air that's inside your lungs here. So that'll be F.9 due to the 0.9 atmosphere pressure in this example when we've expanded our lungs a little bit already to reduce the air pressure inside. So that's pushing outwards, helping you to breathe, the air that's already in your lungs pushing outwards. And then here, the applied force, that comes from your actual muscles that are doing the expansion here. So in order to expand this cavity, to create more space inside your mouth and lungs, your muscles are going to have to provide a positive net force, a force acting over this distance here, the distance over which your chest expands. And so that force acting over this distance is doing the work. So, okay, that applied force from your muscles must be greater than the pressure force difference between the air outside and inside your chest. So that'll be the difference in pressure times the cross-sectional area of this space here, which might be somewhere inside your respiratory system, inside your trachea or your mouth, some relevant cross-sectional area inside there. So in this picture, if we've got a pressure difference of 0.1 atmospheres inside and outside, that 0.1 ATMs times the cross-sectional area inside your respiratory tract, that's how much force your muscles are going to have to apply in order to successfully expand your chest enough to raise water up 1 meter in a straw. All right, so we would say you'd have to be sucking pretty hard to pull water up a full meter, but you could probably do that and maybe even pull it up another full meter with a 2 meter long drinking straw. Although at this point, you're going to have to breathe out and exhale a bit because your chest can't keep on expanding forever. So you'll have to exhale some air through your nose, perhaps, if you're keeping your mouth on the straw. So that allows your chest to collapse a bit, and we let some of this air out. We vent it out through your nose. So now there's less air trapped in the straw, mouth, lung cavity, but we've maintained that lower air pressure of 0.9 atmospheres on the inside. And we're ready to breathe in again, expand this space once again, doing work on that gas again to raise up the water a little higher. So we repeat our cycle here. Now we're going to apply a force on our muscles will apply a force on our chest cavity over another distance to expand that volume in order to reduce the air pressure inside that straw even farther. And now the air pressure outside on the water, 1 atmosphere pushing down, is going to be even greater than the 0.8 atmospheres pushing down on the water inside the straw. So the net pressure force here will be enough to raise up the water even higher until the total weight of the water in this now 2-meter column is equal to the pressure difference times the cross-sectional area. Okay, and the force you're going to have to apply to make that happen is going to have to be now 0.2 atmospheres times the cross-sectional area of your respiratory system here. So even more force you'll have to apply to drop water 2 meters. And that might be about the limit of what most people could do without training. But suppose you wanted to keep on going, you could exhale then, let some of this air out through your nose, keep it tight sealed to maintain that 0.8 atmospheres inside this cavity, and then expand once more. Breathe in again, doing even more work. Now you're gonna have to apply an even greater force with your chest to push out against the surrounding air of 1 atmosphere against an even lower, now 0.7 atmospheres if you want to draw up water 3 meters through your very, very tall, impressively tall straw. Limit